Hello, hello. So let me put a message as usual to the chat. Mm, 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 mm. What are you doing? Tac, tac, tac. Let's wait a bit. Oh, we'll be starting 30 minutes late. Okay. Oh, all right. Oh, uh, so, okay. So I will just put a message. Um, is 30 minutes late. So let's wait 30 minutes then.
Hello, everyone.
Hello, hello. Just to let you know that we have to wait for Milika that's coming in at 30. So that's why in 20 minutes. She put a message, so you can see the chat maybe where I put Milika will be late during 30 minutes. So that's why we are waiting. She has to deal with personal things again. So yeah.
Hello, hello.
Hello, hello.
We need to make one this boot camp in Portuguese here in Brazil, eh?
Oh yeah.
I really want.
Where are you in Brazil? Brazil. How we say Brazil? Brazil.
Brasil, Brasil,
Wow.
Brazil.
Yeah.
In Florianópolis.
Oh, nice.
Yeah, is on one island.
Yeah. Yeah, yeah.
It's not a Brazil. Brazil is a continent.
Yeah.
Florianópolis is one island. But
Mm.
this is Brazil, but it's a joke.
Yeah, I know some people who are going there every time. There's also like a pop-up city, right? Ipe City, something like this.
Yeah, yeah, yeah. It's my friends. Yeah,
Ah, nice.
yeah. And
Is
you,
it
where you from?
France? La
Oh,
France, la
oh,
baguette, le pain au
ah,
chocolat, le
really
petit
nice,
croissant.
nice. I participate one hackathon, Chile's hackathon. You know the
Ah
blockchain Chile?
oui, et in the
Yeah,
stadium?
yeah, yeah.
Wow,
Yeah, I win the hackathon here in Brazil,
wow.
and I won a travel to Paris.
Oh, nice.
Yeah,
Congrats,
yeah.
congrats.
Yeah.
So cool.
Yeah. Pretty beautiful your city. It's
Oof.
like it's like the films that I watch in childhood about the Second War.
Ah, yeah,
It's,
yeah.
oh my God, it's real.
Mm.
Look, this building, it's real, it's real.
Yeah,
It's
it's
beautiful.
like the architecture. Let me share my screen. Uh, oh, wait. It's yes, very old. Let's say try this. Yes, it's like
Yeah,
some building like this every time, indeed, like this. Mm. I was living in Paris during 4 years, for my studies, yes. But there's a pont, l'Arc de Triomphe.
yeah, yeah,
Yeah, yeah, yeah. La Seine. Miali is living there, actually. Um, but yeah, it's quite. In Rome, it's kinda the same thing, to be honest. Rome is like old, all the boulevard, all the buildings, very beautiful too. But what's wrong in Paris is I don't know, the crowd. People are hurry every time, so limit push you in the metro. Yes, we are not so friendly.
yeah. Europe is very, very old. It's very, very beautiful, has beautiful buildings. Here in Brazil, we are very new. Yeah, we have 500 years.
Oh yeah.
Yeah,
Mm,
we don't have very old centers or cities like just Rio de Janeiro and Salvador is
mm.
the most old cities here.
Yeah, I want to plan something in Brazil, around like the carnival in February 2027. So yeah,
Nice.
let's see. Let's see. Will be great.
Yeah. In last year, we organized one big hackathon on
It's that.
Copacabana Palace, Rio de Janeiro, for Stellar Meridian. You know?
Ah, yeah, yeah, yeah. I remember. Yeah.
Yeah, yeah. I organized this hackathon, this educational part. This
So
is
cool.
very yeah, yeah. The
Congrats. Yeah.
Copacabana
Mm,
hotel is
mm.
really beautiful.
I remember, yes, for Meridian. Indeed, Stellars did that in Rio. And this year, where they will go do things, I didn't check at all.
What?
Where
Sorry.
where Meridian will happen this year?
It in here is in Portugal.
Oh,
The first idea is in Qatar, but we are Qatar are
it's
in
not
war.
possible.
Yeah,
Um,
and they changed to Portugal.
okay. Yeah, Portugal, Portugal. This is like a
I'm
big hackathon.
sorry.
No, go ahead.
I am ambassador of Stellar.
Ah,
My
yeah.
beauty.
Like there's some people who are ambassador in South America, for Stellar. Yeah.
Yeah,
Mm, mm, mm. But you know, actually, just Stellar, I don't know at which point it's going to be like sustainable for builders. Like if you are building a project there, at which point you are going viral, you know. Yeah,
yeah,
it's a question. So that's why I'm not going to the this ecosystem, actually. But I understand that in South America, it's the main, not the main chain, but the main builder ecosystem represented, kinda, very active because they have funds to do that. But yeah, at term, I'm not sure Stella will perform at all itself. So that's why I'm not doing things with Stellar, actually, with DevTrack. I'm not into the ecosystem for money, so that's also my issue. Is I'm I'm just trying to help people. And so yeah.
Nice, really nice. Stella has released one big
Mm.
version now about ZK, yeah. Now you can run some like zircons or
Okay.
whatever circuits for in the LE1,
Mm.
and very interesting because it's very cheap,
All right.
and for
It's
me is more simple and secure like any L2 of Ethereum and Web3
mm.
EVM ecosystem.
Yeah.
Is a great player for this year and the next year. It's a good technology.
Okay. Good to know. Like, I mean, but I'm just to know at which point is sustainable. I'm always checking
Oh,
things like this. So I'm like, yeah, I don't know.
yeah,
Like it's very more VC backed, Stellar actually. So when the ecosystem, like the in how to say that, when the world is not going great, VC are are stepping down, and you can see it into the chart. But yeah, I don't know, like um maybe I should give a try. But I'm very selective with ecosystem itself. So that's why like we are doing things with Solana actually. I was doing things with Base last year because Base is very was very open-minded, was very into onboarding newcomers in the space, etc. But not anymore, unfortunately. So yeah, Solana is I think it's here to stay. Mm.
yeah. Here in Florianópolis, we have one base of base. Yeah.
Oh,
It's a beautiful office
yeah, I
that
saw
base
it.
built
Base
here.
brother.
Yeah, yeah. I
I
have
saw that. Yeah.
nice. I have some friends that work with base.
Mm, yeah. It's Guy.
Yeah,
Mm,
Guilherme.
mm.
Guilherme. Yeah,
Yeah. Mm-mm.
the
He's
Brazilian.
leading Latam as well, if I'm not wrong, right now.
Yeah, yeah, yeah. I think that he's head head of Latin. Head of Latin.
Yeah. I think so
The
too.
last year he start like head of Brazil,
Mm,
but I think that now he's Latin.
mm. Nice.
The guy.
Mm. By the way, we are hosting like a hub in Brazil. Uh, tuk for the hackathon. So it's going to be in Sao Paulo and at the garage of Super Team Brazil. So which is nice. Actually, they have a pretty sick space, and there's already someone from the Tupac who is here, by the way, before the hackathon, but um, she's here for Colosseum. So actually, yes, they're running. Let me just share my screen again. Tuk. Yes, they're running that like a space.
Yeah.
That's cool.
Yeah, I meet these guys, the super team
Yeah.
uh, in Argentina. Oh, this guy is very beautiful and friendly guys. Yeah.
Okay.
Uh, I stay with him with they in Argentina for 2 weeks, and oh my God, has have a great heart. I love these guys.
Good to know then. Yeah, I'm speaking with the lead of Super Team Brazil, but not this one. All
Really nice.
right. Um, so I have to take my charger.
Oh,
Is
I will get one coffee for me. Okay. You want one coffee? One Brazilian coffee?
co coffee?
Yes.
I'm not drinking anything on my side. Yeah, I'm quite boring. Like I'm not drinking alcohol, I'm not drinking um wine, I'm not drinking coffee, tea, all those things. I'm a boring girl. So yeah, I'm not smoking. So, yeah, um, you are not boring.
Yeah,
Hello, no, you're not. Can confirm.
yeah.
Yeah, we lived together during a week with Miali in France, in Cannes.
Hi, hi. Nice to meet you.
Hi.
Yeah, we've been together and you're not boring. It's not because you're not drinking coffee that you're boring. Absolutely not. And so many people, drinking coffee, very boring. So can tell.
Here in Brazil,
Actually,
it's very different because everyone drinking coffee. Yeah, it's
I
uh,
love coffee too, and especially in Paris, like always with a mug of coffee and so on. Even though, like in my Carrefour market, just like down in my flat, I can ask for a coffee. I have the butcher in front of me, like I can ask for a coffee. I have the the baker always because for me, like I'm a coffee addict, aficionados almost, but that's fine. I need to stop. I mean, reduce the amount.
where you from me? Mayali?
Yeah, Mayali, from France. I live in Paris. What up?
Ah,
voilà, voilà, effectivement.
Paris too. Okay.
Tuk tuk tuk.
I will get my coffee. One moment, okay?
Okay.
One day at an interview, like someone, like the person who passed me the interview said at the end, "Fortunately, you are not drinking any coffee. You will be like a electric pile."
Yeah, I think that you don't need to have that coffee like you're already like dynamic. But for me, like it's more
Super
about
active.
the taste,
Mm.
especially in the morning. Some of people this is the cigarettes. Not for me, but I mean not the morning, but the coffee, like the smell of the coffee is like I don't know. It's I can't explain. It's irrational.
Yeah. Mm. It's like this, it's like this.
Yes, yes, yes. Whew, my God.
So let's wait 5 minutes.
Yeah,
Just I will approve application. I still have how much? Like 150 almost to take care of.
do you sleep sometimes? Like, this is my
Yeah.
question.
Yeah, you know that you know I wish time I'm sleeping, but I have time to watch Netflix like every day. Like during 2 3 hours I'm watching Netflix.
Lucky you are. Wow. That's so cool. I did not watch Netflix since a few days now. I'm currently in a hackathon. I'm still building right now, but I just take a pause. I mean, I'm proud of what I've built, by the way. The
Nice.
deadline is the weekend, but I'm proud of what I've built, by the way. It's the first time. So, and I'm like I'm happy that my Netflix is bugging. There is something I need to fix, and I did not fix on a purpose because otherwise I could be fucked up, to be honest. So because I want to stay productive
Yeah,
at my
that's
goals,
it. Mm.
and I need to sleep like, oh, quoi que ça va là. I mean, it's okay. It's okay. It's okay now. It could have been worse,
Mm.
but
No, yeah, when it's come to be productive, indeed, cut Netflix. On my side, like I'm starting Netflix around like midnight every time. So after working, and
Mm.
then after yeah, sleeping around 3 4. That depends.
Yeah, yeah,
You remember?
yeah. Of course. Of course. Now, me, like now, I'm driven by Cloud Code rate limits, but I'm optimizing because I found the RTK implementation to save tokens and reduce
Okay.
it. Yes, I'm going to show you. I'm going to show you because it's very interesting to not burn tokens so fastly. And yeah, this kind of strategy
Yeah.
because I only had $20 to spend.
Yeah.
Yeah, that's it. And but it worked. But you need to practice. Sometimes I forget, so I set the token. But it's okay. It's
Mm.
okay.
I hope for the hackathon. I'm trying to get on topic and board, because I'm talking with the startup lead, but like as it's a big company, that takes time, etc. So I'm not sure they will do it on time.
Mm,
But yeah, let's see, let's see.
yeah,
Indeed, right now we are super dependent on building with AI. Like basically,
of course. Yes.
before Akanon was kinda really different.
Yeah.
Like you, you don't have to pay anything, and why no? You are, you have to pay
Mm,
things to make sure you can access like
yeah.
building stuff. So that's so
No,
fucking
no,
crazy.
that's
And
true.
and even if I feel it's removing a buyer, it's also adding one for people who don't have money
Of
as
course.
well.
Yeah, people who can't afford, sometimes it's a pity because now I see
Mm.
I'm investing, in the for AI agents, for Cloud Code, for API, and like I'm not gonna say like my secret sauce about my what I'm building now, but I try and invest on some APIs, well-known APIs. Oh my God, there's like 500 euro a month. I was like, oh no, no, no. It's too
Yeah.
much.
Yeah.
Oh,
I will send an email to everyone to apply for the agentic engineering grant, so which is related to get access to cloud, etc. So it's
yes,
like 200.
yes.
It's for the Solana Hackathon. So
Mm.
actually, they are providing grants only for people who have good ideas, etc.,
Okay,
who can showcase their work. So basically, it's not open to everyone, but I mean, you should give it a try.
of course. All
It's
right.
200. So yeah, let's see.
Yeah. No,
Mm,
but it's interesting. Also, I saw your opportunity about AWS machine learning opportunities from Amazon or something like
yeah.
that.
Mm.
Yeah.
There's a lot of opportunities, but
Yes.
still, every time to pick up the right one,
Yeah,
it's
but it's
something.
very interesting because their courses are well explained, by the way. So,
Mm.
yeah.
Yes, yes, yes. So I will take my charger. Uh, okay. Okay.
Mhm.
Why people ask me for Dev to Pack merch?
Hein? Merch?
Sometimes when I'm reading message, I'm like,
But what they want merch? They
yeah,
want merch from you?
like as someone we attend like a summit, I think at the end of in 2 days, they're asking me if we have Dev to Pack merch here. No,
That's so, I mean, that's interesting, which means that they I still like, at least they love what you do. Like they do love their three packs. But yeah, the merch, like, yeah.
yeah, we will maybe open soon, like a mini store online for Dev to Pack merch, but actually, uh, no, we are not doing things.
Hmm.
Like the only merch we have done was in Argentina. Um, yeah, and it cost a lot to be honest. Like
Yeah.
I think it was 4K. Maybe I put like 4K for 70 people.
70. Oof.
Yeah, and
That's
even like the residency extra, like in Argentina, I spend around like 35, 50, 35, 40K for everyone for a month. So,
Yeah.
but people don't notice that as it's free for them.
Yeah, because they
They don't
don't
do it.
they don't notice, what's behind, of course. Yeah.
Yes. So not everything is free.
Oh no.
Tuk tuk tuk. All right. So I will check this minute. Hey, when are you available? Tuk tuk tuk.
Where 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 are our where do you work, Mieli? You work with coding or design or business?
For now, like I'm still independent. I'm at home now, like working remotely.
Like me?
So this year now I'm in the bootcamp of Dev 3 Pack since the beginning of this year, learning about smart contracts in Solidity and DeFi, and for now ZK privacy. And at the same time, I try to be more expert in AI agents. So I'm doing some meaningful hackathons. Currently now I'm doing so, and I want to create building on chain. This is my main goal for this year, and creating content on Twitter most of the time. So that's it. Like it's
Share your Twitter. Share your
yeah. I'll build like I did mini vlogs during the ATHCC event. Uh,
With tennis.
Yeah, that was the funniest one. And you know what? Most of the people they came to me after and they told me that they that was their favorite vlog. So uh,
Like me doing some shit with tennis.
yeah, that's it. But you know what? I felt that I was exactly with the right people to do this like this. It couldn't have been another way. Melike, you, Jules,
Yeah, my
I mean.
friends.
I mean, everyone.
nice.
Melika is here. Could you hear?
Really?
Yes,
Ah, yes.
yes, here I am.
Hello.
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 How are you doing?
I'm signing papers. I'll maybe purchasing my first home, so it's a bit tiring.
Good life.
What you need, thank you so much. What you need to go through in order to purchase something, a lot of paperwork, and then all the lawyers are so strict with all the rules. They need to check everything. You need to sign
Mm,
20 something papers in one day. I need to look at all of them, and
it's crazy.
it yeah, it is a bit.
Hectic. Yes. All right. So yeah, we were talking during 30 minutes about our life. Yes. All right. So I will give you the stage.
Okay, sure thing. Sure thing. Okay, I will share my remarkable screen. Let's see. You should see it. So again, guys, apologies for waiting on me. It's a bit life-changing event for me right now for signing papers and for buying my first house. But yeah, let me check if this is what I see. I need to share my so far. How did you guys like the previous sessions? Was something unresolved? I don't hear if anyone is talking.
Allô, allô? Allô, la Thérèse et les Martins? They are chatting.
Hmm. Let me check. Yeah, I'm trying to share my remarkable page, but it's not working well. Yes. Yeah. Okay, okay. I see your chat. Super cool. All right. So for everyone that is joining after the session, my name is Milica. I'm ZK Privacy Lead for Dev3 Pack, and also I'm doing PhD research in zero knowledge proofs. So for today, we are having, yeah, thank you so much for congratulations and everything. I'm trying to do the adult thing, yeah. So for today, we should go through
Could you share your
KZG.
screen?
Yes,
Okay.
I'm trying my best. Let's try it out. I'll be sharing, let's say, a new notebook, blank one. Because it's constantly sharing some different notebook. Okay. Let's see if I try with different Wi-Fi network, would that work? Adult things, right? Heard about ZK, sorry, KZG and what it is. What do you guys know about it? Let's see. Anyone, someone? Did anyone read slides from the last time? It included KZG. Yes, no?
I'm not sure they went through all the slides.
Okay. All right. For some reason, Remarkable Screen Share is not working. And
Maybe
well,
you can go back, like end and go back.
yeah, I'm trying it right now. Share again. It's very weird because Remarkable had some changes in the app supposedly. So it should work well, but let's see. Okay. I should present it now. Obviously not with all the scribbles. But do you see it? Do you see this Remarkable page?
Yeah, all good.
Okay, finally. As they say, it worked on my machine, but it's a different thing when we're doing something online. So for today, we're diving deeper in KZG, and we're going to use a trusted setup. We're going to see commitments and evaluation as the last process of KZG. So for For those who have gone through a bit of the slides I have sent, it's KZG Goldberg protocol that has been designed for exchange and evaluation of secrets. And they're using polynomials as a backbone, and we'll use one polynomial so that you will be so that you can try it at home as well. It's going to be a smaller polynomial with a lower order, but you will see the power of algebra and the algebraic backbone, and you will see also, as well as trusted setup that has been used through multi-party computation. We're going to set that up, generators. We're going to use finite fields as well. But something that you need to know about KZG is that in the real world example, it's using pairings check. Here we're going to use evaluation by hand so that you can see how the algebraic backbone works. But usually it would use elliptic curves and the finite field of the elliptic curve and PQR and R prime points on it. Okay, so let's start. Let's see if so for everyone, this is polynomial. You see it, commitment scheme. Why polynomial? You will see that we're going to have even our own polynomial, but usually you would see a polynomial with elliptic curves that we're going to see later on. Okay, so let's start with setup. This is the first step in KZG. By the way, if anything is unclear, you just let me know and we're going to adapt it to you. So for setup, we're going to have a group G. You guys, you have pens and paper so that you can write as well. Let's see, chat. Big party for set up something for run a ZK proof later. Yep. So let's assume that we have a group G that is of order P saying 0, 1, 2, 3, 4, 5, 6. It's going to have a generator 1. That means that you can touch every element of the group by increasing with a step 1. And we're going to have P of 7, that is the order of the group, and also a number of elements, let's say, of the group. See, is there some, I see some question or something? The operation for the field, this is not the field, this is the group. We're going to have field as well. But you can touch, this is setting up for commitment. Field is where the polynomial operates. So there are two distinct things. Okay, so for us, we can say that field is a finite, the field we're going to use is a finite field of a prime order P. Every time a prime order is used in KZG, you're going to see it frequently if you start reading the papers that usually prime numbers are used. And we have covered what they are last week. Also, we're going to have FP, the finite field. That is finite field of order P. All right. And with G as a group, okay, we'll say it is a group. Groups can be they can be multiplicative and additive groups. You can find, we're going to see different versions of it. And in KZG, we'll see as well that the possibilities where sometimes you will multiply it, sometimes you would do the additions, but you need to know that there are two versions of it and that they have properties of both groups that they belong to. All right, so we said, okay, there is the red dot, we love it. We have group G, and that is used for commitments, and FP, the finite field of order P, that is the field where our polynomial lives. Okay, let's define our group 1, 2, 3, etc. until P minus 1. Why is this? Because it is of order P. Okay, let me see. I have written down the polynomial as well, but okay. We're gonna see that later. One thing that we need to do is to sample tau, that is a secret tau, from our field here. So in this example, we can say our tau is 5 for the sake of our presentation. And we're going to use it for calculation of global parameters and then for our checks, but this is something that needs to be deleted after the trusted setup. Let me check. Okay, let's see. I have written down the polynomial we're going to use for the x for the sake of calculations later. You should write this down. Only prover will know this polynomial. Let me just check if there is nothing that is being chatted about in our chat. Cool. All right. So, onto calculating global parameters. GP means global parameters. And GP is calculated this way. HO is G times then, because it's 0 and the order, so 0, x to the power of 0 is going to be 1, so G is conjoined with nothing, it's just plain G. Then we have H1, which is tau times G, and then we'll have H2, which is tau to the power of 2 times G, etc. So because we do have, in this example, we have only order of 2, we're going to stop here. But what would happen is we need to calculate global parameters up to the height of polynomial, meaning that let's say that d is height of the polynomial. That would mean that we would have h d with tau to the power of t times g. And it needs to belong to this field. Okay, so we have the basics of KZG in the beginning for our setup. We have that written down. So this is something that delete after this step. So after we calculate our global parameters, we should forget that tau existed, and we can burn our computer. Cool. Yeah. So let's go to the next part. Since we do have tau, then and also if you see this, sorry, everyone should write down this polynomial that we have, because we're going to use it later. Only prover knows this. Okay. Since we're going to use this polynomial for calculating commitments, and later on with evaluation as well. All right. Let's calculate our global parameters. As we know, our g, tau, and also we know our polynomial. So let's start. Since I'll write down this f of x is x to the power 2 plus 2x minus 1. So let's start with our GP, that H0 is 1. Why? Because we had only, let's see, let's go back. We had only G here and nothing conjoined with it. Okay. Then we have H1. And since we got tau times g, and tau is 5, it is 5. Then we have h2, which is g times tau to the power of 2. And we will have, in our case, we will have 25. But because we have to be within the field of 7, then we need to do modulus of 7. And what would that be? That would be 4. Okay. So we will have 1, 5, and 4 respectively, because we have the height of polynomial that is 2. Okay. So to prove to the verifier that the prover knows the polynomial that we have here, they will make evaluations of the polynomial, and then the verifier will send values. And then we will properly calculate every point of the polynomial, and we'll see in the proper example. Let's see. So, okay. The group that produces the global parameters, they would need to know the height of the polynomial as well, of course. Tau and g parameters, since they would need to know how many of global parameters they need to produce. They need to know the height of the polynomial because of that. Otherwise, we will not have all the all the members so that we can conjoin them with our polynomial later. All right, so let's start with the commitment. So what does a commitment mean? So it is our polynomial that's evaluated at secret G, and but because we do not know secret G, then we will use global parameters, that being the values that the MPC or multi-party computation has sent. So let's try that out. Let's see. So since we have I'll write down our equation in reverse order because the global parameters are being produced in in escalating order from 0 to the height of polynomial. So let's start. It's -1. I'm going to permutate it a bit, but the value is going to be the same. Okay, so let's calculate the commitment of this function. So we're going to write it down in this way: f0 times h. Okay, I'm checking if something is interrupted with remarkable, but it's cool. So plus f1 times h1 plus f2 times h2. So this is what the prover calculates, right? Because they know the polynomial. And since so these f0, f1, and f2 are values that are conjoined next to the let's say x to the power of 2 has coefficient of 1, but x to the power of 1 has coefficient 2, and x to the power of 0 has coefficient -1. So how does that look like? What we're going to have is, see, what we're going to have is -1 times, because h0 is 1, it's going to be 1, plus we have 2 times h1 is 5, and we're going to be plus f2 coefficient is 1 times 4. This is what we got right here. So we are writing down these values, h0, h1, and h2. We're combining them in a commitment with coefficients of the polynomial. All right. So let's calculate what we have. This is -1 plus 10, not 16, but 10. 10 plus 4, what would that give? It would give 13 modulus 7, it will result in 6. So that would be the commitment to this polynomial. So for us to check it, we can evaluate this polynomial at the secret tau, but that is not what the prover should calculate. It's only for us. But yeah, let's try. So let's see if this actually works, as in producing global parameters with tau and g, and combining global parameters with coefficients of our polynomial, creating commitment. So does that actually work if we're using tau instead? So let's see. So let's calculate function in tau. So let's try it out. So that means it's function in 5. Of course, it needs to be within the modulus 7 as well. So that would be -1 plus 10 plus 25 modulus 7. What would that be? It's 9, 34 modulus 7. That would be 6, right? Okay, so now we are ready for the next step of evaluation, but we have proven this connection between global parameters and with secret tau. And with commitment to the polynomial. The thing is, tau is never used in this step. It's just for us to check it. But yeah, like I've seen questions, but I cannot jump every time. But like, why is it called f of tau? So this is function in that point, function in point tau, which is which should serve as a connection to see if we have calculated commitment of function properly. So it's only for us to check it. In the real-time scenario, tau is being deleted after the trusted setup, and no one is looking at it with the global parameters being set after. All right, so later on, let me scroll a bit. We will have evaluation. So in the process of evaluation, the verifier should send some value, and then the prover is going to calculate commitment. Let's try, let's see. So you guys remember when we role-played prover and verifier with hashes, and yes, then you were sending a proof that you have calculated a hash properly by sending different numbers that would hash to certain value. So this is how this is very similar how prover and the verifier talk, to say so, by sending challenges which prover needs to answer on it. So let's see. Suppose, oh, sorry, I have touched the wrong button. Let's suppose that U is something that the verifier sends to the prover. Okay, so let's say verifier sends U. Okay, so the task of the prover is to calculate function in U, in point U. So let's start with it. Function in U should result in value V. we're going to use this later to find zeros of the polynomial. But for us, what is important is that our verifier is challenging us to find the root of f prime function. So what are we going to do? Since u is root of f prime, then we're going to calculate it this way. F minus v, then we'll say that x minus u divides f prime. How would we write that down? That's minus v. And later on, we'll see that we're going to have quotient polynomial. That is important for us to write down. This q that you see is quotient polynomial, and f prime that is here is going to have its zero in u here. That is why we have written it like this, written it down like this, since it is going to be the root of f prime. All right. Further on, let's calculate first the function in u so that we can calculate v, right? Here. So first of all, we need to put, let's see, where is our, we need to find, okay. Our polynomial is here. I need to write it down from time to time. So it's minus 1 plus 2x plus x to the power of 2. Okay. What does that mean for us? Because we are trying to find value in the point u. We will start with minus 1 plus 2 times u is, because u is 4, then we will have 8 plus 16. And since we need to do modulus, we need to be within that field. Then what would happen is this is 7 plus 20 plus 16 is 23 modulus 7, which is 2. Okay, so the result of the function in the point u should be v. So this is it. So v is 2. So for today, we're having a lot of calculations, but everything will come to its place once you try it at home for a couple of times. You will see how smooth it can become. All right, since we do have v now, we will say, okay, f prime, and we need to find f prime is f minus v. And because we know this function here, then we would say it is minus 3 because it's function minus 2. So we see minus 1 here, and we're going to subtract 2 as well. So it's going to become minus 3 plus 2x plus x to the power of 2. Let's see. Okay. Yes. Yeah. U is the root of that function f minus v, which is f prime. You are correct. Yes. Cool. People are following up what we're doing. Cool. So now what we need to do is we need to find quotient polynomial, which is not going to be sent by the prover or the verifier, but the evaluation of the quotient polynomial will be sent, and that's something we'll call witness. So since we know that our f prime function is quotient polynomial times x minus u that was previously sent, then we can say that our f prime is our original polynomial minus v that is being calculated as the value of our original function in u. Then we can write down our witness polynomial in this way. Okay, so we can say that this looks like a G. Q of x times x minus u. We can say that due to our previous calculation, I'm going to slide it down. So we see it here, correct? Since this one is equal to this one, we can write that down. Okay, and we can write it down like this, minus v through and through minus u, and this is our witness polynomial. We have already calculated this one. Q out of x, it's this one. So it's minus 3 plus 2x plus x to the power of 2. And then we have x minus 4 that the verifier is sent. And once we deal with this, equation, and we're going to end up we're going to end up with x plus 6 after modulus applied. So our quotient polynomial will be x plus 6. If we want to calculate commitment of the quotient polynomial, that being witness, then we can do evaluation. Since this one, as you see, has only height of 1, so this is x to the power of 1, and this is 6 times x to the power of 0, then we're going to have a height of only 1. Let's try it out. Commitment of Q is commitment Q of 0 times H0 plus Q1 times H1. So we need to go back to our original values, H0 and H1. Let's see. Okay, it's 1 and 5. So we will say that since this one, we can say this is the constant that is next to x to the power of 2. So this will be 6 times 1 plus, this is what we can think of it as like 1 times x. So it will be 1 times 5, because h1, if I'm not mistaken, is 5. Yes. What we would have here is 6 plus 5, 11. Modulus 7 is 4. So commitment of Q is 4. Cool. And what we have here is witness value, and this is what is sent to the verifier. So the witness value that we have calculated is the object that convinces the verifier that the claimed evaluation is the result of the function within the value of u that the verifier previously sent, and is consistent with the commitment quotient that we have, that being q out of x. Let's see. So the point is, like, I'm looking at the question. The point is that our verifier is going to challenge us if we know the zeros of the polynomial in this case, and if we do not have it, then we'll have some partial numbers that could not fit. In the real KZG, this is done through pairings check, but here with us, we need to find zeros of the polynomial. Cool. Anything else? Okay, so the global parameters and the trusted setup is being done by multi-party computation. After that, you won't be able to say tau to know anything about it and have any knowledge of it. And neither prover or the verifier should have any knowledge of tau. They know only the global parameters, and what would the prover say is, I will tell you that I know a secret function that I will prove to you that I know it and I can do the commitment to it. That's that part of binding that we have seen before when we were speaking about zero knowledge proofs, that binding is very important, that we need to commit to something, to either some object like we did with the safe box, or we need to commit to certain function now that we have the polynomial. Okay, so the prover is calculating the commitment, then the verifier is going to send challenges, and they would be sending some use. So we're going to see to send back a result that is fully within the zeros of the polynomial. But yeah, like if the prover actually does not know that, he would send back fractions and not round numbers. But yeah, because KZG is meant to be within the elliptic curve, we would not be able to convince the verifier that we know it. But if the polynomial evaluates to zero at some point, then that point that we have sent divides it exactly without fractions that we have seen. Okay. All right. So now we should try. Oh, touch something again. So we should do evaluation now as well as if we were the verifier. Okay. So let's write down the verification. But yeah, like one another thing that if our divisions were wrong at any point of time, the verifier would catch it because we would have the remainders and the verifier could not verify it. Yeah, so let's start with the calculation of verification as well. Let me check it. Okay. All right. All right. So, as we mentioned before, it is always the weight on the prover to calculate it, not on the verifier. Most of the times you would see the verification is very succinct, very small, while proving is a tedious process, like with doing the commitments and proving that to the verifier with challenges. But on the verifier side, it should be fairly short. So let's write that down. So how we're going to check as if the verifier would do. So we'll in this example we're going to use tau, but that is not how we're going to use it every time. But the tau should be deleted. But let's check the if it's algebraically correct. So if we put tau minus u that the verifier sent on one side times commitment of q, it should equal commitment of f minus v, that is being value in point value of a polynomial in point u times g. Again, this is not something, this is not how the verifier would check it, because the verifier would definitely not know tau, but commitment of q. And but let's check if this is correct. So our tau was 5, u was 4, commitment of q was also 4. Commitment of f was 6. V was 2 and g was 1. So it says 1 times 4 is 6 minus 2, which is correct. And at this point of time, this equation would be satisfied, and the verifier would be convinced that the prover had sent proper commitments. But yet again, in real time, in real world, this would be done with pairing check on the elliptic curve. Let's see the check. Yeah, so for so unfortunately we don't have a bunch of time. We would need group theory, we would need number theory for this to be comprehended fully. But what I can recommend is this is something that is considered the backbone of zero knowledge proofs, that you can understand it. Then for sure you can go through this multiple times until it gets to you fully. But yeah, like I would send you the original paper after this class. You will receive original paper, I can send you also the additional materials on how to study the group theory, the number theory. And the fourth thing I have prepared as well is an article on different zero knowledge proof types that you can read on, that is a bit more digestive than this math. So what I'm trying to do is to have some math and then something easier to go through, especially that weekend is in front of us, and then will be you can read something that is more advanced zero knowledge proof, as in ZK snarks and ZK starks, and also you can try this KZG math as well. What I would like to see as well is writings on the paper and posting that in the group so that we have some proof that you have done some zero knowledge proof. So guys, what questions do you have? Please take the mic. I know first time I have seen this, it was puzzled. It was puzzling, but yeah, like I'm there for you. And for me, what worked is going through this multiple times and seeing how commitments and group parameters, global parameters, and the groups that we have and the finite field works. So it's definitely a big chunk to chew on in an hour and a half, but for sure it would be something that is interesting to go through.
Sorry, actually, it's quite complicated matter,
Yeah,
and
yeah.
I still don't understand how it works, but uh, I'm going to read the paper you're going to give,
Yeah,
and
yeah.
hope it will work for me.
Yeah, sure. It's there are two things that you can do. Is one is going through this. That's why I asked you guys to write down everything, and of course you will have this session recorded as well. But things will get clearer every time you go through it. For me, it worked that way, and for other people as well. I will send you the white paper, the paper that is behind KZG. But what I would recommend you first is to go through these equations a couple of times so that you will show up with more understanding of the process. Why I'm saying this is because if you take a look at the paper, for me, it's a bit confusing. Why? Because they have used different notations in different parts of the paper. I'm a person that needs consistency in order to understand that. And yeah, but any questions you have, I will be there for you and answer that in the shortest amount of time possible. So don't you worry.
Okay. Please, I understand this a bit dense. So in terms of like the prerequisite topics, I know you mentioned finite field. Can you give insights into like maybe how much of finite fields you need to understand to like actually implement this, or if they're under building blocks you need to like fully grasp before going through them?
So for finite fields, that's why we had exercises with modulus and applied it in hash and everywhere else. So for finite fields, you don't need to understand much, but you need to know that every time the, let's say, answer to your calculation, so the result is going off the chart. So you can think of it. Let me share my screen again. Let's see. I will write that down. Share, present with screen share. Okay. Mhm. Okay. Where is it now? Okay, I will show you how it looks like. The finite fields are, they are the, for me, interesting, but they're very simple. Let's see, I'm trying to scroll. Okay. So, you know the coordinate system. Let's see, no, you stay here. So this is X, this is Y. And then let's say this is finite field and we will work within, let's say, hundreds on both sides. So if we say that anything passing this 100, it would need to come back in a way. So let me, so it won't be perfect, but I'll show you one elliptic curve. So let's say that it looks like this. And then you think of it like, what happens here, right? Well, it just continues back here. And then it continues here. That's how it works. So it needs to fall back within this finite field. Or anything like if you have some point, right? And you want to do addition on this elliptic curve, you would need to find a way to come back, because if you go off the chart, to say so, then you would need to come back. So finite field is just, we're not working with infinity anymore, but we're working with some space. You can think of it as if you're doing some sort of calculations on your computer, and then you have a buffer of certain value, but you cannot go over that buffer, but you need to come back to it. Of course, here is 0. Yeah, it's a bit, yeah. It is a bit complicated, but you'll get there like I did. I was clueless before, but as everyone was, right? But for us, sure, I will. I'm thinking I'll be providing you yeah, for sure, like 4 to 5 must-read research papers. Yes, and then having that sent to you. Number theory as well, group theory. But yeah, like it is difficult if you didn't study it before, but That's why we're trying so hard with all the examples we have to make it easier for you guys. Anything else you guys want to add?
Any question? Not easy session. I remember last time we we had to do more extensive things. Yeah. Ah, question.
Could
Uh,
you please go back to the place when we um, decide that f of uh, f of u minus what I forgot it minus v uh, it
Mhm.
divides by what x minus u, right?
Mhm.
Why why is it?
Why is that? Because we need the challenges to find zeros of the polynomial. That's why we are subtracting that value.
Uh-huh.
Mhm.
But why is it a zero for the polynomial?
Well, it is easier for verifier to check that way because otherwise, if we do not know zeros of the polynomial, it will be sending fractions back.
You mean that the verifier uh, selects the number which is a zero of the polynomial.
It
Or
should
what?
be, we should find with that number, verifier is challenging us if we know zeros of the polynomial, or if we can find zeros of the polynomial. So another question was, is this similar to the method elliptic curve?
What? I'm sorry.
Uh-huh.
How do we choose that polynomial?
How do we choose a polynomial?
Yes.
So yeah, so it should look something similar to this in most books that I have read, but there are actually like safe polynomials that can be used where it is checked that they don't have weak points, or for example, that you can find a mirrored dot, but not the tangent on it. So, for example, if there is a way to calculate certain dots by reflection of it, but this is for elliptic curve cryptography. But if we cannot find them by reflections on the other side of the curve, then we can do tangents on on our curve, and yeah, it's then you need to find proper polynomial that can satisfy the properties of the curve.
I think I need to understand elliptic curve cryptography first, because I understand that this curve is not curve actually, but it is considered a curve in an abstract way.
Mm-hmm. Yeah, it's a bit advanced what we're seeing now, but you guys deserve good treatment, so you guys should see this as well.
Okay, waiting for your papers.
Yeah, I'll be sending them to you guys.
I have a question.
how you encode the data to do the commitments in the curve?
So this is for what we have seen. This is a polynomial commitment scheme. But later on, I'll send all the papers that are explaining everything else.
Okay. But my question is related to the polynomials because I understand I think I understand the math, etc. But how you put that in a real environment, how you create the polynomials, like that kind of stuff.
Okay, I'll send you I'll send to all of you guys pairings check and elliptic curve. I think you have asked for that. Yes, I think yeah. Someone asked, yeah, Adri asked for that. So I will send because it's a bit advanced for everything that we're doing, but still I will provide it as well. No worries. So one of the things is we are having elliptic curve cryptography here. We're having polynomials that are being selected for polynomial commitment scheme. So you will have pairings check as well. So it's I will send you and then you can munch on it a bit, but it will take a couple of hours. Yeah, no worries. No worries. Super cool. If that is all, I will be preparing materials for you. I'll be sending a bit of zero knowledge snarks and starks to you guys, and all the additional materials that you have requested. So buckle up and be as hardworking as you are over this weekend.
Can I ask a question? In the beginning, you showed that we calculate global parameters first. So in the new examples, how big, how long are that set of global parameters?
So you would need as many global parameters as the height of your polynomial, because you would need to conjoin every value of constant conjoined with the parts of your polynomial and evaluate that with global parameters. So whatever is the height of the polynomial, you will use as many global parameters.
Okay, thanks. Thank you.
No worries. That's all that we had for today.
That's all. All right. Yeah. So we see each other again next week. Then I think it's just the next week who you are teaching again. Yes. Like during 3 weeks, so we already done 2 weeks. So yeah, see you next week.
Yeah, you're going to see Circum,
Yes.
something that's more practical for you guys. Better programming, and yeah, then also we'll set some time apart to discuss a bit about what you have read and about KZG as well.
Perfect. All right. So thanks a lot again, Melissa, for everything, all the content, or your expertise on that, teaching to others. Very beautiful. So yeah, let's say see you next week, everyone, and
Yeah.
take care. Have a nice weekend.
See you on Tuesday.
Just bye.
Bye bye.